if that's okay. And
just for volume, are we good? Okay.
and is everybody good online?
I can talk very loud about the mic.
Okay.
The mic is
No
gonna be
one's-
online.
No, yeah, well, the owl, yeah.
Yeah. Okay, great. Well, thanks for coming out in the middle of the busy prep week for AGU here. Our speaker today is Vincent Ledvina, who's a space physics PhD student at the University of Alaska Fairbanks. His current research is focusing on auroral beads and plasma processes responsible for causing auroral substorms. And today he's going to be talking to us about cutting edge projects in Aurora participatory science. Thank you.
All right. Yeah, thanks for the introduction. My name is Vincent Ledvina, second year PhD student at the University of Alaska Fairbanks, and I'm really passionate about citizen science, about aurora chasing, and excited to share that with you all here today. So just before I begin, thanks to Doug Rowland for inviting me here to give this seminar, and also to all my co-authors on the talk who helped me prepare this. So here's a quick outline of what I'll be talking to you about for the next 40 to 45 minutes. I'm going to try and leave some time at the end. I know it's kind of an hour block, but I'm going to try and leave some time at the end for questions in case you all have any. I'm going to be going over sort of, the whole idea of this talk is the cutting edge. So I'm going to talk about a lot of recent developments in the citizen science world in relation to auroral physics and space physics. So first I'll kind of set the scene, right? Citizen science and heliophysics. Then I'll define exactly what I mean by quote unquote citizen science. And the term citizen science, the actual term citizen is under debate right now. And I'll talk about the sort of four main projects that I want to highlight, which are Aurora Source, Aurora, Upper Midwest Aurora Chasers, and Rare Auroral Phenomena is kind of just a catch-all for all the really cool work that Aurora Chasers and citizen scientists are contributing to the study of things like seas, star arcs, fragments, all these types of things. And finally, I want to wrap everything up and contextualize all this in this framework of agile collaboration. So a little bit about myself. I'm up in Alaska, up in Fairbanks. I got into this field through aurora chasing. So actually, when I was 4 years old, I saw the aurora for the first time in 2003, the Halloween storms. And I grew up in Maplewood, Minnesota, so Twin Cities. And I remember actually, seeing these dancing curtains of aurora all across the sky. And of course, I was 4 years old, so I didn't go to grad school the next year. But I think, I think that experience really embedded this love for the outdoors and the natural world, which then, has remained with me for the next, 2 decades. And I was introduced to aurora photography, which is what set everything off through Aurora Source. So Aurora Source, you all probably know the project. It was 2016. There was a pretty decent chance of seeing the Northern Lights. And I saw a lot of people on Aurora Source were reporting that they were seeing the aurora near where I was located. So I went out with my dad and I took a photo of the Northern Lights. That's really what got me hooked. So now I'm up in Alaska. I'm also an intern at aerospace. I'll be doing my 3rd summer there. And again, really passionate about citizen science. Auroras, my thesis is really, focusing on auroral beads, but I want to kind of weave in a lot that you can do with citizen science into that. So the motivation behind why we care about citizen science and heliophysics today is that we're facing a lot of these grand challenges in the field that are requiring new and novel ways of doing science. And you can do science with large efforts and volunteer activities. Citizen science, this helps solve big data problems. So of course, now we're dealing with petabytes of data, whereas 20, 30 years ago it was terabytes. And that's, a big challenge because if you're trying to find needles in haystacks, you can either do an ML or AI algorithm or, even better quality is creating a citizen science project. You can also use those data to train these ML and AI algorithms as well. Now, citizen scientists and aurora chasers participants are also gathering their own data. So this is what I'm going to be talking about mostly here. You have people out in the field actually reporting data that then scientists can use and collaborate with these citizen science to work on. And citizen science projects themselves are also collecting unique data and discovering things as they're going, which may have not been realized before. And so then, this is really all accelerating scientific discovery through the lens of agile collaboration, which I'll touch on later in this talk. And of course, citizen science is an opportunity to teach and engage the public in space weather research. So I just want to draw your attention to these two figures here. The top one is actually three sort of data sets or three different things you're seeing. So the first one is that gray swath is a satellite that was flying over the Aurora Oval during the May 10th, the Gannon storm. And as you can see, the Aurora Oval is pushed all the way outside the field of views of those red circles. Those are scientific grade all sky imagers, the T-REX and Themis ASI networks. And usually they're very well positioned to study the Aurora because they're up in the Aurora Oval. But during this extreme event, the Aurora Oval was so far south that it was not in the field of view of any of these imagers. So in order to study this May 10th storm, we need to rely on where people were seeing the Aurora in the photographs that they were taking, which are these green dots. Now on the bottom here, this is very new sort of data that I processed. These are Aurora reports as a function of time. So you may not be able to see this, but this is a sort of, it's clicking up. And this is the October 10th storm. And you're seeing, you can almost map the Terminator, the day-night Terminator as it sweeps across. As soon as it got dark, you had people seeing the Aurora all around the world. So it's really cool. I'm really fascinated by these extreme storms and what we can do with mapping, Aurora chasing, and the data from just ordinary people. And to sort of illustrate that, now we're seeing all the studies coming out. This is one that I helped out with the Arctics team. So shout out. I don't know if Bea is watching or listening, but she's also involved. It's a team of international researchers as well as citizen scientists that are really, we're really passionate and really devoted to using Aurora chasing as sort of this driver for discovery. So what we did is we ran a survey. We collected over 700 reports of Aurora during the May 10th event, during the Gannon storm. And we also plotted the naked eye visibility of these reports, which allows us to then compare with historical records as well. So, if you go back to the Carrington event and these earlier events, you have newspaper clippings of, sightings of Aurora. Those are all naked eye reports. So it's really important to get that naked eye visibility. And just from looking at the different colors being seen, you can derive different, properties of the different particles coming in. So red auroras are typically associated with really low energy particles precipitating down into the atmosphere. So you can easily see that in this histogram here, lots of red aurora being seen as well as rare auroral phenomena at the very bottom left there. Those are all reports of steves and star arcs and even dunes. So it's really interesting. You can get a sort of idea of when the aurora was being seen. If you plot that on a sort of dial plot with MLT, a lot of reports kind of early in the night. Now, that could be because people go to sleep. I don't usually go to sleep that early, but, and then you can also see these reports coming at the main phase of the storm as well. Now, this study is really great because it shows just how far equatorward the aurora was seen, down to 23 degrees magnetic latitude. So, and it also encompasses all of the sort of large databases of auroral sightings during the May event. So you can see here, or maybe not, it's kind of an eye test, but these little gray dots are reports that actually one of my friends compiled just on his own, scraping social media, over 2,000 reports of the aurora. And you can see that it really, almost the entire world saw the aurora. So it's just really cool the way that citizen scientists, the way that aurora chasers are helping us characterize this really extreme event. And of course, it's not just these two studies. In fact, now there's tens of studies that are releasing. It's going to be really cool going to HSD next week, seeing all these presentations. This is another one that I thought was really inspiring. Taking these backyard observatories that people have, this one's in Missouri, and actually looking at the RGB ratios of the colors in the image and backing out some different properties like, for example, the electron density over these locations and mapping out, for example, TEC over the entire US and figuring out when you have these large substorms, these big spikes in TEC, and you can correlate all sorts of data and create these really high dimensional data sets with citizen science data. And so this is kind of, this isn't all happening in a vacuum either. I'm talking about citizen science, and really what we're seeing is an unprecedented time where people are really caring about our field. So what we're looking at here is Google Trends data for the search term space weather. I'm not sure if you've all used Google Trends before, but it's kind of interesting. What you can do is put in any search term into this website, and you can see the relevance of the search term over time. So this is space weather, and it's a relative scale, so 0 to 100, 100 being the most relevant that search term has been whatever time period you're defining. So this is from October 2004 to April 2024. And then if you overlay the solar cycle, you can kind of see, maybe a little correlation there. And if you do the same thing for Aurora Borealis, now you can see a lot more spikes. And what I did was I actually checked archives and I was able to pull large storms for a lot of these spikes. So this was a KP6, this was a KP6 here, KP8 over here, KP7. Now, a lot of times the spikes are not correlated with these big geomagnetic storms, but maybe the big paper got released and the news picked it up or something. But it's kind of cool to see over time how relevant these things that we're studying are. Now, if we include the Gannon storm in this time series, if we widen that bracket of time to include May and June and July, August, all the way up to now, because remember, we were just looking at October 2004 to April 2024. Well, here's what Aurora Borealis becomes. So you can see all those big spikes we saw up to 100 are now flattened out pretty much. So I think this really, indicates how present our field is in the public right now. I think the iron is hot and we need to strike. So here it is for space weather. And, a lot of people saw the Aurora this year, obviously, seen all over the world. But there were also a lot of really bad news articles that came with that. So there was a lot of hype, but there was also, people taking advantage of that hype. So, now we have all this presence, all this public kind of awareness of our field, but we need to do this as scientists, make sure that only the right information is getting out there. So, I think citizen science is part of this answer. Of course, it's not the solution, in and of itself to the issue of misinformation, but citizen science projects can do a lot of really good work with educational elements built right in. I think that's a really good way to get started. If you're not comfortable going on social media and being this person that's out there public facing, you can do a lot of this work through projects in a more formalized way. And what's great about that is that projects can sort of spur a lot of this discussion and keep it going in sort of this positive feedback loop. So we see this all the time in the Aurora chasing communities, is you have projects like Aurora Source, for example, putting out educational materials, providing the resources for people to communicate with each other, with the subject matter experts. Then those people that are educated then kind of become ambassadors for their communities, go out and sort of spread the message of the science that we're doing. New discussion takes place, and then the science questions that were, initially in the project become even more focused and even more narrow and more specialized to what really needs to get done. So it's really cool. So now about citizen science, the sort of formal definition is organized research in which members of the public engage in the processes of scientific investigations by asking questions, collecting data, and/or interpreting results. And as you can see there on the screen, there's a lot of different ways that we do citizen science. It's not just Aurora Source, it's not just an online project. It can be physically interacting with your environment through, taking a photo of the Aurora or going out, in the field, literally in the field, taking photos of plants or animals, reporting that. Or it could be scientists going inside classrooms, collaborating with educators to inspire the youth. There's a lot of different ways that citizen science gets done. But a quick note on terminology is that the term citizen science, that doesn't encompass everybody, right? So just keep that in mind that as the field evolves, we're realizing that, we're not being entirely inclusive in the way that we describe citizen science. So I just wanted to say that, we're sort of transitioning to either participatory or community science and to be more, encompassing of different people all around the world. However, if you hear me using citizen science, I'm not excluding, these other terms. That's just what I'm familiar with. So principles of citizen science, not going to read them verbatim, but one that I really want to hit on is that one main principle of citizen science, whether that's projects or whether that's directly collaborating with people, is making sure that you give your participants the credit that they deserve. So, especially with Aurora chasers, we go out and we spend hours and hours, not only learning how to take the photos, but also how to read the data, how to watch the data, and then physically going out and taking them is a chore. I mean, it can be -40 in Alaska, and you're spending 30 minutes just to bundle up, to go outside, and then you're braving the cold, you're spending money on gas, you're losing sleep. So, it's really important if you're using Aurora chaser data and you're collaborating with people to acknowledge that a lot of work went into that, a lot of actual physical work. And that's called reciprocity. So there's different reciprocity efforts that are kind of common in the field, which includes co-authorship of papers, but even, just, publicizing people's photos, like if you, advertise it on the NASA website, that goes a long way for a photographer. So, just keep in mind that a lot of people are volunteering their time to do your science. So it's important that we acknowledge that. So here's some cutting edge projects in Aurora citizen science that I want to cover today. The first is Aurora, and then Aurorasaurus, and the Upper Midwest Aurora Chasers. I'm going to start with Aurorasaurus, which is actually a project I interned for in 2020. So I've really, I'm talking a lot about Aurorasaurus because it's really been a big part of my career so far. So in case you're not familiar with Aurorasaurus, it was founded by Dr. Liz McDonald, and Laura Edson is the project manager, and Liz is at NASA. And it really helps answer the question, can I see the Aurora? And the sort of crux of the project is that on aurorasaurus.org, Aurora Chasers report whether or not they've seen the Aurora by filling out a quick form that includes metadata such as the direction the Aurora was seen, type of Aurora, auroral activity or motion, and of course, people can submit photos as well. And all these reports get mapped alongside the Ovation Prime auroral oval model. So that's really good for validating how well these models are doing in real time, as solar wind is fluctuating around, but also as the auroral response changes as a result. So here's just kind of an example. Here the form. So of course, you can select different colors like red, green, white, or pink. And here's what the site looked like during the Gannon storm. So a lot of reports. They received over 5,000 reports that they're cleaning right now. So a part of this process is these reports get logged on the Aurorasaurus website, then they also get cleaned manually by a team there, to make sure that the data are reliable for scientific, studies and publications later down the line. So I think they're planning on releasing these data sometime this year, hopefully before 2025. But it's really cool to see. You can actually see this view line here, this red line. This is part of the Ovation Prime model. And in case you're not familiar with Ovation, it's kind of this model that takes in solar wind, and it's an empirical model, and fits it to like the average statistical auroral oval response. So a lot of the times it works really, really well, but during big geomagnetic events, when there's not a lot of data to fit to, it can become semi-unreliable, and especially trying to pick up, very strong variations in auroral activity like substorms doesn't quite catch those. So you can see that even though the view line is pretty far extended here, you still have auroral reports coming in as far south as Cancun, Mexico. And what's a really unique feature of Aurorasaurus is that when there's clusters of reports near the view line, that view line will actually modify to encompass that cluster. And people who are registered on the site, aurorasaurus.org, can receive SMS alerts when people see the Aurora near them. So it's a tool for Aurora chasers, obviously, because what's better than using a proxy data source like solar wind or magnetometers while actually having people on the ground seeing the Aurora. So it's a crucial tool for me. It's a crucial tool for thousands of other Aurora chasers around the world. And like I said, ground truth auroral visibility is just much more reliable. I would rather have somebody saying, yes, the Aurora is out, and they're 10 miles away from me, than trying to look at all the data and maybe making a guess as to whether or not I can see it. But Aurorasaurus is much more than just a reporting tool. It's also building communities through the ambassador network that's been going out for, I think, almost a decade. And I'm part of this ambassador network. I joined when I was an undergrad, and that really got me connected to a lot of subject matter experts, but also other Aurora chasers. And a fun story about that is I met my current roommate through Aurorasaurus. And I actually went up to Alaska in 2021, my first time in Alaska in October 2021. And I went Aurora chasing with him. And that's really, that was one of the driving factors for me to move up there and really end up at UAF. So this ambassador network is great for connecting researchers, educators, community leaders together, so that researchers can help these Aurora chasers know, like, here's what kind of imagery we need, here's what you should be telling your communities. And then those community leaders can go and sort of translate those scientific questions down to a level that their audience may be able to understand. But besides the ambassador network, Aurorasaurus also has semi-annual reportathons, which are really popular. We just had one where I think almost 50 people joined. And, it seems like every single year we're just making these longer and longer because people don't want to leave. It's like just a fun hangout. I mean, I see people that I don't see for the entire year at these events, and it's just fun to catch up. These journal clubs also help translate, the science articles that we all know and are sort of the basis for our science down to a level that the public can understand, right? I mean, a lot of the science, the Aurora science obviously matters for Aurora chasing. It's just a lot of people don't know about that because it's hard to understand. So these journal clubs are really helpful. And of course, there's a newsletter, which you could sign up for if you wanted to, where all these different events are communicated. Aurora Source does a lot of work educating through Infiniscope, and as well as on their own website, on their blog. So there's a lot of different resources. I helped create the Aurora card game when I was an intern, and this 3D printed magnetosphere is a great tool to use in the classroom. So here's just an example. This is their blog. They have a lot of interesting articles, not only about auroral phenomena and the science behind the aurora, but also making the process by which data are released, cleaned, and made available to scientists transparent to their participants. So making sure that the audience and the aurora chasers that are putting in the work know what's happening to the data. That's really important. Having that transparency with your community is crucial to retention. So I want to talk about Aurora, which is a really exciting project that was started by Jeremy Kazoo just a few years ago. And I'm one of the beta testers for the Aurora. So I've been taking care of one of these units for the past couple of years up in Alaska. If you're not familiar with the project, it's a portable all-sky imager designed for easy deployment by aurora chasers to record time-lapse imagery of rare auroral phenomena. It's all consumer off-the-shelf or COTS technology, which is really great because a lot of these scientific cameras and a lot of this gear you might give to somebody, but they have no idea what they're doing, right? I mean, if it fails, they have to call somebody. They don't know how to fix it. Well, you can, and it's actually by design, open this thing up just with 2 little clips and dig around in there and troubleshoot if you need to. So it's really nice. And what's really important about this project is that you're producing science quality data. And by science quality, obviously it's not necessarily filtered imagery, which is what scientists like, but it's high resolution, high time rate, white light images that most importantly are geo-located and also have accurate timing. That's really, really important. If you're relying on aurora chasers to collect data for you, you need accurate timekeeping. So we're doing this because if you remember that plot I showed in one of my earliest slides of all those all-sky cameras with the aurora sort of outside the field of use, well, how are you going to capture the aurora then? Of course, you can rely on aurora chasers, but it really helps to have just a unit that you can deploy that's doing everything automatically in the background. The idea behind the Aurora is that it doesn't get in the way of your normal photography workflow. You get an Aurora chaser, they shouldn't have to mess with it. It should just be a set and forget type of thing. So the idea is that while we have these great all-sky networks, there are gaps, like actual gaps in between the field of views, just normally. But then of course, during geomagnetic activity, you have the Aurora extending equatorward, and potentially interesting auroral phenomena like seeds or star arcs happening equatorward of the auroral oval. So it's nice if we could sort of make the system of observatories available to citizen scientists during these big geomagnetic events. Also, aurora chasers are mobile. So how many times have you been looking at all sky imagery and you find a really great event and only 2 out of the 16 cameras actually have clear skies? Well, aurora chasers can go and find those clear skies. They're not fixed to a location. That's really important. And consumer off-the-shelf technology has also just come a long way in general. And it's really important for studying these fine-scale features in the aurora, which can help us understand how they're created. So inside the aurora, you have just a basic Raspberry Pi controlling an APS-C 24 megapixel RGB sensor with an f2.0 fisheye lens. You have accelerometers, a GPS inside to get your orientation and position and timing. And everything's designed for aurora chasers by Jeremy, who is an aurora chaser himself. So, imagine it's -4, you have big bulky gloves on. Well, that's why you only see a few buttons on the outside. That's all it takes to operate this thing. It's so that you can do that with really thick gloves on. You don't have to take off your gloves and get frostbitten to, set your shutter speed or take an image sequence. Inside, there's an SSD that records all the images. And then as soon as you connect back to Wi-Fi when you're back home, those images go right to the cloud automatically. And you can even monitor things in the field with a little Wi-Fi access point. So I've done this when it's really cold. I have the Aurora set up somewhere in the field. I'll be in my car warming up, but I can connect to it and see the images coming down and making sure that everything's good. So the data are processed in this software called DaVinci Resolve, which is a video editing software very familiar to Aurora chasers. It's a free software actually. And how it works is if you ever used Premiere or After Effects, these other softwares, you plop in your image sequence, then you can sort of add these nodes that sort of incorporate different elements, these different metadata right into the time-lapse sequence. So things like a keyogram, which wraps around the outside of the image, a time counter in the bottom right, your different, latitude and longitude and things like that. That's really important because we want this product to be as accessible as possible. So then we share these data on YouTube. So the Capture North YouTube channel, and that's really nice because you don't have to futz with some API or some server. If you're an Aurora chaser or a scientist, you just want to see an event. You just go to the YouTube channel and watch the image sequence, watch the time lapse, and if you think that's interesting, then you just email Jeremy and he'll give you the full, the full sequence of images. What's also cool is that since it's on YouTube, it can really easily be integrated into other things. So Ilko Dornbos is a really cool space weather timeline viewer, which plots the Aurora data here alongside other data from like Omni, like the Omni Web database, so solar wind, also magnetometers. You can throw a super mag in there. You can throw in the Themis ground mag stations. So it's really powerful because, at least for me, whenever I'm trying to think about, what's the next thing I want to study, I think of these really interesting events. And I'm just constantly searching through, the archives, and I want to find all these different data sets to compare it with. Well, you can do that here by just going to this website and looking at all the Aurora data alongside all these other measurements. So it's really a high dimensional data set and viewer. Videos are also converted to GIFs to report on Aurora source. And then Jeremy's been experimenting with these cool VR, virtual reality, augmented reality demos. If you scan that QR code, it'll pull up a YouTube video, which you can actually see you can move your phone around and see what the Aurora looked like when I was recording this sequence just earlier this year. So here's one of the observations. What's important to note is that since Aurora chasers are operating the Aurora, we're really only recording when it's worth recording. So, if you've ever done studies with all sky imagery, you're just sifting through a lot of garbage data. Nothing's really going on. It's a quiet Aurora, or there's clouds, not much is happening. I would say all of the Aurora sequences that are on YouTube are something interesting, like it's worth actually looking at. And this was one of them here. So Jeremy was out, I think this was near Yellowknife, and he recorded a quiet time Steve. And I'll talk about Steve later, but what's unusual about this one is that Steve usually appears in the subaurora latitudes. And Yellowknife is around 65-ish, I want to say, in that sort of normal auroral oval magnetic latitude. So it's really unusual that we saw this Steve, and luckily Jeremy was out and recorded, otherwise we may have not had observations of it or even known about this event. So Bea and others published this paper earlier this year that characterizes that event and which used Jeremy's data. So what's next for Aurora? Well, I think kind of next on the list is kind of, integrating this project. Of course, it's still a prototype, so, it's not necessarily quote unquote ready for release. It's not a commercial unit or anything, but Jeremy definitely has plans. And one thing that would be really cool is, having this in sort of these citizen science campaigns. So if you had a geomagnetic storm that you knew was going to happen, like this May event we saw earlier this year, well, why not, ship 10 Auroras all around the US and gather data, in response to that forecast. You can also do that with just missions that are happening now, or proposed missions like MAX or Cinema. Putting these Aurora cameras in areas that you can then correlate with space-based data. There's also a smaller, low-cost version in the works for fixed locations called Aurora Mini, and of course, Jeremy takes into account all the feedback from the scientific community as well as Aurora chasers when he's making new designs, new iterations of the Aurora. So we're definitely looking to collaborate and hear all your thoughts about this project and what it could be used for. I have a poster on Monday at AGU. I actually have the Aurora with me, not like in the room right now, but I will be taking it to AGU. So if you want to see it in action, definitely stop by Monday afternoon poster session. So I want to talk about the Upper Midwest Aurora Chasers. It's a Facebook group of 28,000 plus Aurora Chasers. My friend Tanya Melnick is one of the admins. And there's tons of these Facebook groups all over the internet. But what makes Upper Midwest Aurora Chasers unique is that there's an active agile team that's really, really has their space weather chops. They're actually at a space weather workshop earlier this year. And, just Facebook groups in general are really interesting. There's sort of these nexuses of big, really prime community sort of leaders and super users in the Aurora world. So if you're a scientist looking to collaborate with Aurora chasers, look at these Facebook groups, find the admins, and they could be, people that you collaborate with to find other people who may be, collecting data or have data that you want to use. And what's unique about UMAC is that they also release these sort of space weather updates whenever there's a big, event coming along the way. As well as they've been doing this Aurora apps review. So, many of you may not be aware, but a lot of the data that NASA and NOAA put out are not only used for operations, these real-time products, but are integrated into commercial third-party apps. Maybe you might have an Aurora app on your phone that uses like the Ovation Prime model, for example. But it's something that a lot of scientists don't know is that there's $1 billion market out there taking these NASA and NOAA, these freely available data sets and turning them into products that Aurora chasers rely upon. So it's interesting just in and of itself, that aspect, but then surveying your community and really understanding, what people are using these apps for, I think is really interesting. So Tanya Melnick and the other admins surveyed, all of their members and got a bunch of responses that kind of highlight what Aurora chasers are kind of hungry for, in these apps. So I'll just read them here real quick. So like I said, the majority of these apps use official space weather data products from NOAA, NASA, SIDC. Many of these apps rely on the Ovation model. So if you've ever seen, a little notification pop up, you have a 2% chance of seeing the Aurora in your current location. That's taking it straight from the Ovation model. So it's kind of interesting how that gets baked in to these different notifications. And several, these apps are really advanced too. I mean, in the commercial space, you have a lot of interesting development going on. Taking these, we're going to see in a little bit, but these magnetometers and sort of developing substorm forecasts, and you can track like the substorm current wedge and the location of that as the substorm is progressing. And really, I think what's important here is that these Aurora chasers are becoming smarter and smarter. These apps are teaching people space weather and teaching people how to use the data. And when you're dealing with the public, it's often, really easy just to sort of say, oh, well, they don't know anything. But these apps are making the data that we scientists use on a daily basis more accessible. And so here's one of these apps called Glendale Aurora. And I won't go through everything in detail, but it takes these magnetometer arrays all over the world and uses some proprietary algorithm to basically issue substorm alerts. So you can see here, we all know about nanoteslas. I mean, it's a very familiar unit to us, but it's right in this app. And there's even a little tutorial online for quote unquote how to use a ground-based magnetometer. So kind of like magnetometers for dummies. I actually learned how to use a magnetometer with this site here. So there's a full-time developer working on this app. This is one of the apps that UMAC surveyed. What does this all mean? Well, first off is that online Aurora chasing communities are research nexuses. So you can join these communities yourselves. I think it really benefits scientists to join these communities and really have a presence to the public, have a sort of online presence that makes you more trustworthy, it makes you more familiar. If you ever want to collaborate with Aurora chasers or other people in sort of these public spaces, it really helps to have a face to the name. If you contact somebody and say, hey, I'm really interested in your data, well, they might recognize you from some Facebook group since you're a member. There's also sort of Discord channels. There's all sorts of different avenues that people are interacting and meeting. And if you're a researcher, one potential action that you might take from knowing all this is that when you develop a real-time tool or data set, you may want to reach out to one of these app developers and say, hey, can I demo it in your app, and then get feedback from the public that way? Because I know a lot of us do have to release our data for the public. It's mandated in some way, shape, or form. So kind of a unique way of doing that is sort of validating whether or not your data set is approachable, even to other scientists, would be to reach out to these app developers. So I want to talk about rare auroral phenomena. So kind of taking a turn here, and how Aurora chasers are contributing to their ongoing studies. So I'm going to mention Steve. I'm going to talk a lot about Steve, but also you may have not heard of some of these fragmented aurora like emissions, a ROGDO, or red aurora with green diffuse arc, and of course dunes. So Steve is what I call the viral citizen science story. It's strong thermal emission velocity enhancement. Of course, all these phenomena, they're not new. They weren't discovered. I mean, we've had auroras, we've had these phenomena for potentially millions or billions of years, as long as Earth has had a magnetic field and the solar wind's been blowing. But they haven't been realized and really thought about until recently with the advent of all these consumer off-the-shelf cameras and the sort of excitement of aurora chasers and realizing their impact they could have on our field. So the first images of Steve were taken in 1911 by Carl Stormer. But then in 2018, aurora chasers started noticing, this phenomenon a little bit more, especially in the Alberta aurora chasing community. Steve typically appears after what's called a substorm expansion. So the aurora goes through this really intense period and, gets really bright and kind of dances around. And during the recovery phase after that, if you're looking at the aurora to the north, Steve will appear off to the east and to the west as this white or purple arc. And right below Steve, this is actually a weird case. You usually get this picket fence feature, which looks like field-aligned auroral rays coming down. Those are green. So these citizen scientists in the Alberta aurora chasing community said, this is really interesting. And they started taking photos of it. They started looking at the literature. They said, this looks like a proton arc. Then they went to scientists, and the scientists said, no, you cannot see proton arc. This is not a proton arc. So they went back and said, okay, it's not a proton arc. Well, what should we name it? And they came up with Steve. So that's where the name came from. And if you've ever seen the movie Over the Hedge, that's where Steve comes from. So it's not a quote unquote aurora per se, but an auroral phenomenon, because the actual process by which Steve is created is potentially not precipitation. It's actually sort of how you heat up a metal and it gets really, really hot, like white hot. That's sort of the same mechanism. It's just such a hot and fast flow of gas that is heating everything up and creating this continuum emission. So citizen scientists, aurora chasers, have been very influential in the study of Steve, particularly through analyzing the small features seen in Steve's picket fence and the actual structuring within the sort of broad array of Steve across the sky. So this is just one study I wanted to highlight here, is the mysterious green streaks below Steve. Because what can sometimes happen is you get these picket fence features that extend down beneath this arc, and you get like a messy exclamation point with these little feet coming off the side, not field aligned, sort of perpendicular to the fields. So now we have the whole family and friend network of Steve. We have, of course, star arcs have been known about forever, but we now know that star arcs can evolve into Steve's, which was, written about in collaboration with citizen scientists down in the southern hemisphere. And we have other weird things, like we have blobby kind of auroras, weird secondary electron emissions from proton aurora. We have Rogda, which is sort of a manifestation of that red aurora with green diffuse arc. And we have auroral dunes. So this is not necessarily related to Steve, but if you have a gravity wave that propagates up from the lower atmosphere to the altitudes of a sort of what's called a proton aurora shelf, it can modify that shelf in these striations that you see here. And those are likened to sand dunes. Fragmented aurora-like emissions are my favorite. They're like green Tic Tacs. That's kind of what I call them. And they can form at seemingly any time. Steve is typically seen in the substorm recovery phases and some aurora latitudes, but fragments are almost seen more often than not polewards of the aurora oval, and typically during substorm expansion. And we don't know necessarily, under what conditions or when these FAEs occur, but we're currently working on collecting more observations. So that's part of the science that citizen scientists can unlock, is just knowing when and where these phenomena happen. And so I'm part of this Arctics team, this ISI working group. We've developed a lot of resources, not only for citizen scientists to know how to take photos for science, but also for scientists to know what the best ways are to interact with communities and interact with aurora chasers and how to collaborate. So if you're looking at learning more, we have not only have this handbook, which is great, but also this field guide. I just want to shout out Katie Hurlingshaw and Donna Locke. So Katie Hurlingshaw is a researcher up in Eunice, in Svalbard, and then Donna Locke is one of my friends. She's an aurora chaser. They did a lot of work making sure that this came together. So shout out to them, and of course, the rest of the Arctics team too. And Katie's also involved in this really interesting mission that you may have not heard about. SpaceX is launching the Fram-2 rocket with, it's a crewed module that's going to be polar orbiting. It's the first time we've ever had polar orbiting astronauts. First time ever. And there's going to be somebody on board with a camera looking for aurora, looking for these rare auroral phenomena, imaging from above. And what we want to do is have aurora chasers on the ground imaging from below, so we can sort of figure out this 3D structure of these rare auroral phenomena and get different vantage points. So that will actually be happening soon. It's supposed to launch in March of 2025. So it's the Solar Max mission. And this kind of gets into this idea of citizen science campaigns. I think this is really interesting, is that as we're, if you're a PI of a mission or you're thinking about a mission, whether it's a satellite or a sounding rocket, think about the added dimensionality that citizen science data could give to your results, to your science. And think about, which communities you can touch and really lead deposits in that not only benefit them, but also benefit you. So, of course, we have the upcoming Solar Max and, as well as EASY with the EASY Mag project, but, we have missions in phase A, Cinema and Max, as well as sounding rockets that could be a potential sort of relation to all this. So to wrap things up, I want to contextualize everything I said in this framework of scientific agility and agile collaboration. And the idea here is that everybody possesses an innate ability to do science through just our natural abilities as humans to recognize differences in the continuum or patterns. And you can use that ability in citizen science projects. For example, a lot of projects revolve around looking at time series and finding little spikes. But in terms of heliophysics, aurora chasers are really, really good at spotting these differences. If we're out taking photos of the aurora, we notice something is weird, we're going to start recording and we know that's weird. We know, even though we might not know the science and why it is, that what we're seeing is different and potentially scientifically interesting. So this innate ability, this agility of people can be incorporated into projects and should be thought about if you're designing a citizen science project, is how to harness that natural ability of these people. And of course, people have a lot of different skill sets. Not all of us are scientists. Not everybody in the public is going to be a space physicist. But when you talk to a lot of these aurora chasers, a lot of them, have PhDs in other fields or, advanced degrees in, electrical engineering, but all of them have some sort of technical background. It takes some sort of expertise to take an aurora photo. You have to know about images. You have to know how they're taken. And, these concepts of light and exposure, photons, it kind of automatically tunes them to have some sort of scientific background. So I invite people to, look at these aurora chasers as collaborators and not just people that you extract data from. I think we should be keeping that in mind, that people have contributory expertise. They can contribute things to projects, and you may not realize that, but people have a lot of different perspectives that are beneficial. And of course, citizen scientists, aurora chasers especially, have experiential expertise. We're out in the field looking at the aurora potentially every single night. We've seen it thousands of times, many times more often than scientists. So if we say something is weird, don't necessarily say, well, you don't know anything. No, we see the aurora a lot. So, if a citizen scientist, if an aurora chaser says, hey, look at this image I got, I think it's really weird, sit down and take that seriously. And you all can participate. I think there's a lot of different ways that, this community, this crowd here in the room can really become involved. Potentially the easiest way is by creating a citizen science project. So there's a lot of different project builders out there, such as Zooniverse. And of course, there's tons of benefits to doing citizen science through projects, which I outlined earlier, but, I think it just feels good, right? And I mean, more literally in a lot of brands, there is this broader impact section. And, I personally, when I was applying for fellowships and things, I included a citizen science project in that broader impacts, and that really helped me out. And I think that that's, not only are you doing cool science, but leaving deposits, leaving impacts in the community is really important and feels good. And of course, leveraging and building communities is one other way that you can do citizen science, actually reaching out to people directly or sort of doing your own, ad hoc, or I don't want to say guerrilla style, but, kind of collaborative on a more one-on-one or, group to group basis. That can be done as well. And of course, I mentioned this earlier, but being respectful and providing reciprocity for these people is really important. So with that, I just want to, say that this discussion is not over. I don't want it to be over. If you're at AGU, definitely come and find me. I have a couple posters. And also, I think this is really interesting. There's this Frontier Special Edition here about the heliophysics mid-year education and public outreach efforts. And if you're, interested in working together on a paper or some sort of submission, definitely let me know. So with that, that's all I got. Thanks for your attention. Questions?
Yeah, questions.
Yes.
Yeah, thanks for being here. I'm a big fan of your Instagram account as well. But I was just curious, do you partner at all with like the indigenous communities of Northern Alaska and Canada? Like they must have their own sort of like history, folklore. Do you do anything with that?
Yeah, that's a really good question. It's something that I personally want to do more of. I don't think I do enough. UAF has a really good program. It's called the Cultural Connections Program. And I mean, I've done this where I've gone into different native communities and given like these mobile planetarium talks. And they really enjoy that because the stars in the night sky are really important to them. So UAF does do a lot of those efforts, but you know, it's and I will say I do know that when we're launching rockets in Alaska, like UAF is involved, there are efforts that go into place, especially if we have researchers, which will be in these native communities, you know, taking photos of whatever is being released by these rockets. There is an effort that goes into making sure that, you know, we're basically providing what we need to make up for that burden for them. So, yeah, I think that's a really important subject, but people can always be doing more, I think, yeah.
If there's any questions online, either feel free to put them in the chat or raise a hand or unmute as you prefer.
Especially.
So I noticed that, a lot of this is North American centric.
Yeah.
And part of that's because there's not a lot of lands, for down in the southern hemisphere, but, are there any citizen science projects that you know of that are like in Australia, for instance, or New Zealand or Tasmania?
Yeah, so that's a big challenge, right? Is that the Aurora is not just over North America. I know that in Europe, there's the Sky Warden reporting platform. So it's similar to Aurorasaurus, but it's a little bit different in the way that they make their data publicly available. So Aurorasaurus tends to wait and clean their data before releasing, whereas Sky Warden mostly just you know, these data are available right after people submit usually. But yeah, in terms of citizen science in the Southern Hemisphere, that's something that I need to look into more because I'm not aware of any major projects. I know that there's been collaborations, like I was talking about the Star Arcs earlier and the Star Arcs turning into Steves. That was actually a collaboration with a Southern Hemisphere researcher. Sorry, Southern Hemisphere Aurora chaser. So yeah, I'm not super aware that there's a whole lot going on in the citizen science world in Australia and New Zealand, but I am probably just unaware, so.
The Servers Handbook by Neil Davis.
Yeah, I would thought, yeah. So there's this, it's, I think an Aurora Watcher's Field Guide or something like that, or handbook by Neil Davis, which is a really good read, actually. I think it's a little bit, I would say it's 20 or 30 years old at this point, but it still holds up. I mean, it's just great. And it gives a lot of great explanation into the different auroral forms and kind of what their causes are, which I think is one of the most common questions I get on social media is like, I'm seeing this weird spiral in the sky. What is that caused by? And it's really hard to give an explanation of that without going into the advanced stuff. So, yeah.
When I was mentoring students here, I give them several books about Justin Wolfers and Wilson Gordon, and also Neil Davis.
Yeah, that's good. Yeah, that's good.
So that, I think you showed a slide where there was the picture of Aurora in Namibia.
Yeah. Oh, it's, yeah, one of my first ones, yeah.
Yeah. Now, I understand that, you know, in the storms like the Ghana storm, which was significant, right? It has drawn a lot of interest because many people were able to see the Aurora actually for like maybe the first time. Now, in terms of your instrument distribution, I don't know how you're planning to do the portable instrumentation. I believe that there will be a lot of people who will be excited to have those instruments. But then my concern is when, the side, solar side, dies down and they're not able to see anything. What's the plan there? Do you have any ideas of how you're going to do the instrument distribution?
Yeah, well, I mean, the goal is to get it done sooner rather than later. So there's still a few years left of the solar cycle, I think, which I personally, my bets are that we're going to see another Gannon storm. I think we're going to get another one. And there's research that shows that, as we're descending, you tend to get some more extreme space weather towards like the descending phase of the solar cycle. So I think we still have time, but that is a concern is like once we're at solar minimum, if there is, let's say, funding or these projects come to more sort of greater fruition, is whether or not we're going to have any space weather to capture. But I don't think I'm too worried about that right now. We still got lots of time to go. So.
Yeah. So, yeah, you talk about the solar minimum and stuff like that.
Yeah.
Would there be other use for these types of cameras, like meteor tracking or
Yeah.
something like that?
Yeah, so OSTBot actually has all sky cameras all over the continental United States, or the lower 48, and those record airflow. So it's possible that these all sky cameras, especially the Aurora Mini, could be used in sort of this capacity to sort of measure other things in the sky.
Any more questions?
And just because we're gonna be at solar minimum doesn't mean this won't happen still.
Yeah.
A chance.
Yeah, and there have been some extreme, if you actually look back, I actually hid the slide in this presentation, but you can, in this paper, there's a sort of timeline of extreme space weather events, and it is possible to get, a big event at solar minimum. It's very unlikely, but it has happened before, so never know. Yeah.
What would you say is sort of the biggest unanswered question that citizen science is taking these data can help
Yeah.
answer?
I think the biggest, okay, so, if I had unlimited money, let's say, what I would do is look at all the data that Aurora chasers have captured during the Gannon storm and use software to do image triangulation on all of these images and figure out like the 3D structure of the Aurora oval over time. And that would be really cool. You can also take, and you have to figure out sort of like the response curves of each camera and how sensitive they are to different sort of wavelength channels. But taking the RGB, you can get different information about the electrons coming down into the atmosphere, like the characteristic energies of those particles by taking ratios between different color panels. So if you could do that to some degree of accuracy with, let's say 5,000 images, maybe you could get, like as a function of time, the energy of the electron precipitation in the Aurora during the Gannon storm. I think that'd be really cool. Just in general, I think consumer off-the-shelf technology, you can take TV rate 24, 30, 60 frames per second video of the Aurora and get sub-kilometer scale sightings. I mean, that's pretty incredible. So you can do things like optical flow on videos of Aurora, like these auroral arcs usually have really fast flows within them, and they're usually too fast to resolve, with normal, quote unquote, normal, like all sky cameras. But these white light cameras that people can buy on Amazon for $4,000 can do it. So it's pretty cool. Yeah.
Quick question, Vincent. The instrument you're talking about, you said it's something portable, easy
Yeah.
go into the field and just connect the wire. So are you operating on just the battery?
Yep, so the Aurora operates just on 2 anchor batteries. You can either do it just off of one, just a normal, like $30 Amazon anchor battery, yep.
There are temperature restrictions.
I think there's like a nominal temperature range, which I've definitely gone inside the range. And it was good. I think I've gotten it down to -45 Fahrenheit, and it's been fine. So
But how long did it last?
it lasts the whole night. So what you can do is just, so this is kind of weird, but what I'll do is I'll just take a hand warmer and I'll put it in a sock and then put it inside the Aurora just to give it a little bit more heat. Or you can kind of give it this like little dress, which is like a little reflective, like, those emergency blankets. You can get like a thicker one of those and just drape it over, and that keeps in the heat really well, so.
Great. Well, if there's any more questions, thank our speaker again.
Thank you all.
Yeah, that's it.
Can we